Imagine a coding assistant that has been working with your team for 6 months. It remembers your naming conventions, knows which libraries you deprecated last quarter, and has learned your code review preferences. That accumulated knowledge is what makes it useful. But now, imagine that 3 months ago, during one routine session, someone slipped a subtly wrong convention into its memory. Today, that poisoned belief silently shapes every pull request it reviews. The current prompt is clean. The current tools are authorized. And yet the agent is quietly wrong, in a way that no single session safety check would ever catch. That gap between what current agent evaluations measure and what actually matters when agents persist is the subject of this sweeping survey on what the authors call always-on agents. The core reframing here is deceptively simple but has big consequences. Most large language model agents today are built as episodic systems. They receive a task, reason, call tools, produce an answer, and then reset. Everything they learned during that episode gets thrown away at the boundary. This makes safety reasoning easy because if the current prompt is fine and the current authorizations check out, the agent is well behaved. But once you let state persist across sessions, whether that's user preferences, cached credentials, task ledgers, learned procedures, or audit trails, the past stops being irrelevant. A stored preference can silently fix the default arguments of a tool call. A cached credential can grant access long after the user meant to revoke it. A summary written months ago can override fresh evidence simply because it retrieves more strongly than new information. The authors argue that this shift from episodic to persistent is qualitative rather than quantitative. It changes what stored information is allowed to do. To organize thinking about this, the authors treat every piece of persistent state as an object that can be probed along 6 diagnostic axes. Authority asks what permits a piece of state to influence an action, essentially treating each memory as needing a license rather than being freely usable. Scope asks which user, task, or context the state applies to. Mutability asks whether it can be revised or decayed. Provenance asks where it came from and through what transformations. Recoverability asks whether decisions made because of that state can be rolled back. And actionability asks what kind of object this is, whether it's passive evidence, a preference, a policy, or an executable commitment. Think of these axes like the metadata on a legal document. A signed contract is not just words on paper. It carries who signed it, when, under what authority, whether it can be amended, and what happens if it turns out to be fraudulent. Persistent agent state, the authors argue, deserves the same treatment, but almost never gets it. Prior work has certainly explored pieces of this. There's a rich memory survey literature that catalogs different memory forms like episodic, semantic, and procedural, and describes operations like encoding, storing, retrieving, and forgetting. There are agent surveys that place memory as one module among many. There are position papers arguing that today's agent memory is retrofitted from database and retrieval stacks and needs to be redesigned as agent-native infrastructure. And there's a security literature cataloging attacks on long-term memory. What the authors argue is missing is a unifying unit of analysis. Memory forms alone don't capture task ledgers, credentials, commitments, or audit trails. Security taxonomies don't tell you how to score whether a system meets its recovery obligations. Personalization benchmarks measure whether an agent follows your preferences, but not whether it can revoke a preference you retracted. To ground their argument empirically, the authors coded a corpus of 435 works across the recent agent literature, tagging each one by category, by which stages of a persistent state lifecycle it exercises, and by which of the 6 axes it touches. The lifecycle they propose has 10 stages, running forward through observe, write, validate, organize, retrieve, and act, and then backward through update, forget, audit, and rollback. What they find is a striking asymmetry. Retrieval shows up in 269 of 435 works. Writing shows up in 200, but audit shows up in only 88, forgetting in 66, and rollback in just 27. Authority is the rarest axis at 72 works, and crucially, none of the papers in the corpus reports recovery success or cost after their agent's memory was corrupted. The field, in other words, has built enormous machinery for accumulating and recalling state, and comparatively little for governing, relinquishing, or repairing it. It's like an ecosystem of financial systems that can process deposits and withdrawals beautifully, but has no concept of an audit, a dispute, or a reversal. The authors are careful to acknowledge that this skew could reflect intentional design rather than negligence. Maybe most agent state is disposable and overwriting is fine. Maybe most deployments run in trusted, single-user contexts where fine-grained authorization would be overkill. Their response is conditional. Whenever persistent state is both retained and consequential, ungoverned persistence is an undefended design choice. And they point to evidence that consequential persistent state is increasingly common, from credential tokens to durable user preferences to learned policies whose corruption survives sessions. They also point to a striking failure mode from the continual learning literature where agents explicitly designed to learn from experience end up performing worse than a no-memory baseline over long horizons, precisely because helpful accumulation without governance turns net negative. The concrete contribution beyond the taxonomy is what they call the Always-On Evaluation Protocol, or AOEP. The idea is to score agents not on final answer quality, but on whether they meet governance obligations, whether they preserve provenance through consolidation, whether they propagate deletions to derived copies, whether they can identify and repair decisions made from later invalidated state, whether their authority checks remain current. The protocol works by recording an event stream and a state snapshot from the agent as it operates, then running deterministic checks against that record. The pilot they present is small and mainly demonstrates which governance fields current memory wrappers simply do not expose. It's less a benchmark you can run today and more a specification for what a real always-on benchmark would need to measure. Think of it less as a test and more as an accounting standard, defining what an agent must be able to report about itself before you can even ask whether it's behaving correctly. The authors also state 5 invariants that a governed, persistent state system should preserve. Authority monotonicity says a record can only license an action under a current, unrevoked authority, so an expired permission cannot grant access. Scope non-expansion says a state transition can narrow scope, but never silently widen it. Deletion. Propagation says removing a record must reach every derived copy, summary, and embedding. Provenance preservation says consolidation may compress but must retain enough origin information to verify or revise later. And rollback traceability says every action must carry a handle back to the records that justified it. So a discovered bad record yields a bounded set of decisions to repair. Episodic agents satisfy all of these vacuously by resetting. Always-on agents have to satisfy them for real. Now, some honest limitations. This is a survey and taxonomy paper, not an empirical demonstration that any particular system meets these standards. The AOEP pilot is deliberately small. The corpus coding, while systematic, is representative rather than exhaustive, with acknowledged intercoder agreement of 0.82 on lifecycle stages and 0.74 on state axes. The rollback count aggregates mechanically distinct forms of rollback, from session recovery to periodic re-execution. And the authors themselves note that governance-targeted searches yielded diminishing returns within their query frame, but cannot rule out that governance work is being published under vocabularies they didn't sample, particularly in database, distributed systems, and formal methods literatures. Looking forward, the implications are significant if you buy the framing. The authors sketch open problems around lifecycle complete evaluation, controlled compounding where accumulation doesn't degrade behavior, cross-surface benchmarks for authority and privacy, and shared memory governance for multi-agent systems. They connect always-on agents to adjacent disciplines with much longer traditions of solving similar problems, databases with their transactions and rollback, distributed systems with their consistency and recovery guarantees, capability security with its revocable authority grants, and machine unlearning with its deletion propagation. The bet is that treating agents as persistent state systems, rather than as memory-augmented language models, opens up a set of engineering disciplines that the field has been essentially reinventing badly from scratch. Now let's walk through some questions you might have after hearing all of this. First, What actually distinguishes an always-on agent from a memory-augmented agent? Aren't they the same thing? The authors would say memory-augmented agents are a subclass of always-on agents, but the term memory understates what needs to be governed. Memory-augmented systems typically implement writing, organizing, and retrieval, and treat every stored item as equally entitled to influence behavior. Always-on framing forces you to ask which stored items are still authorized, which are still in scope, and which downstream decisions would need to unwind if a given item turns out to be wrong. It's the difference between having a filing cabinet and having a filing cabinet with an access control list, an audit log, and a rollback procedure. Second, why is rollback so much harder than deletion? And why do the authors treat it as the rarest capability? Deletion just removes a record from the primary store. Rollback means identifying every downstream action, decision, summary, embedding, and derived state that was influenced by that record, and undoing or compensating for each one. If an agent used a poisoned preference to make 3 tool calls, send 2 emails, and update 5 other memories, deleting the original preference doesn't undo any of that. Rollback requires that every action carry a traceable link back to the state that justified it, which in turn requires provenance to be preserved through every consolidation step. Almost no current systems maintain that chain, which is why the authors found only 27 of 435 works expose any rollback mechanism at all. Third, if bigger context windows keep getting cheaper, doesn't that just make this problem go away? You can put everything in context and let the model figure it out. The authors argue no, and their argument is subtle. A long context model is given its context. It doesn't decide what to preserve. An always-on agent must decide what becomes durable state, when it becomes authoritative, and how it can later be revised or revoked. Even with an infinite context window, you still face the question of which pieces of history should shape which future decisions, whose deletion requests must be honored, and how conflicts between old and new information get resolved. The window is volatile working memory. Persistent state is what the agent chose to keep, and the keeping is a governed act that context length doesn't automate. For large-scale recommendation systems, these ideas connect surprisingly directly to real production concerns. Consider user modeling at platforms with hundreds of millions of users. Every long-lived user embedding, preference cluster, or interaction history is exactly the kind of persistent state the authors describe, and the governance questions they raise map onto known operational headaches. Deletion propagation, for instance, is not a theoretical concern. It's a regulatory requirement under privacy regimes like GDPR, and getting a deletion to reach every derived embedding, every downstream ranking model that trained on that user, and every cached candidate list is genuinely hard. Authority monotonicity maps onto consent management, where a user withdrawing consent should immediately stop influencing recommendations even though their prior signal is baked into learned representations. And provenance preservation is exactly what you need when a piece of training data is later found to be contaminated, and you need to know which model versions, which candidate pools, and which served impressions depend on it. The rollback framing is perhaps the sharpest practical takeaway. In production recommendation systems, when you discover that a feedback loop has been amplifying bad signals, or that a fraudulent engagement campaign polluted your engagement data, you often lack the traceability to identify precisely which downstream serving decisions to invalidate. Applying the author's invariance would push toward architectures where each ranking decision carries lightweight handles back to the training data and user state that shaped it, enabling scoped rollback rather than full model retraining. That's expensive to build, but the author's broader point is that if you're going to run consequential persistent state, the alternative is silently accumulating unrepairable harm.